Okay, hi everybody, and welcome today. My name's Aaron. I'm going to talk about a little bit about GoToTen. So I see some familiar faces, but maybe some new faces here. So for those who are new, a bit about GoToTen. It's by this Internet Stiftelse, and they use this place as a free co-working space and an event space. So if you want to become a member, you're welcome to do so. We're open from 8 to 4:30, Monday to Friday. And you can come here to work and or meet people. We have a coffee bar that's just open, so you're tucking into the sandwiches, so good to see. And we're an event space as well, so if you want to do your events like this, you can also do that. I'm going to pass you on to Frida now. She's going to talk about today's event, so welcome, everyone. Okay.
Thank you. Welcome to all of you, whether it be online or here at GoToTen, to today's Tech Tuesday. My name is Frida Enebro, and I work as Communications and Events Officer at Linköping Science Park. Tech Tuesday is a collaboration between Linköping Science Park and Combitech, Ericsson, SICK, NIRA Dynamics, and Sectra. The event is held around every third Tuesday. But sometimes we invite a special guest, and that is what we have done today. Elliot Gestrin is a student at Linköping University, chairman of the university's AI and Robotics Association, FIA, and has worked for NFC this summer. Today, he will talk about AI and whether the data we use to train our AI really is as safe as we think. If you have any questions, feel free to ask them afterwards. And those of you who are online, just write your questions in the chat and we will ask them for you. This presentation will be recorded and put on our website later on. Elliot.
Yeah, and it seems like people are able to hear me, yeah? Well, perfect. Welcome here, everyone. I'm here to talk today about AI data leaks, what that means, and a review of the state-of-the-art methods. So, before we start, however, what actually is AI? That's a very broad, nebulous word that can mean pretty much anything, depending on who you ask. Asking people around me, I'd get answers like ChatGPT or Siri. But depending on context, it could be anything from Google Street Maps to the Terminator. But today, I'll be referring to neural networks. These are a form of combinations of digital nodes and links between them, which send information between themselves in a way similar to the human brain. And depending on the way these connections are made, you will get different results from the AI. Can be anything from generating images like Stable Diffusion or writing text like ChatGPT or recognizing what's in images. And as said, it's the connections between these nodes, which is so very important. Depending on what the connections are and how strong they are and how they're connected, you'll get very different results. And the key to finding the correct connections between these nodes is what's called training. Training in this context means that you show the AI a whole bunch of data. Perhaps it's images that you've collected of cats and dogs. And then you hope that it learns from this. You essentially give it an opportunity to look at the data and rewire its own brain to fit the data better. And just a quick mention, while I'll be talking about AI in sort of living ways, talking about brains and stuff, that's not really representative of how AI actually is today. It's not alive in any real world of the sense, but it gives a good feeling for what I'm talking about. Either way, during training, we show the AI a whole bunch of images or a whole bunch of other data, and it looks at this and tries to rewire its brain to fit as well as possible. And during this training process, we hope that it learns to see the underlying information in the data. It learns to generalize and recognize new breeds of dogs in images we haven't shown it before. Or it will be able to handle new and different situations. This is a concept called generalization, and it means that the AI is good at dealing with new unexpected situations. This is where data comes in. The more data you have, the better equipped the AI will be to generalize and learn different things about it. So more data generally gives a better autonomous system. But with that said, let's look into a small data leak scenario. So let's say you're running a company, and for one reason or another, you're training an AI. Perhaps you're training an AI to recognize different types of breast cancers, or you're training a system to recognize blood on crime scene photos. Whatever it is, it's something based on sensitive data. Data that you'd really rather was kept within your company or your organization, but which you need to use to train the AI to be able to handle the tasks you want it to do. And during the process of training your AI, you show it all this data, and you hope that it will generalize, like I talked about before, in a good way. But for one reason or another, some part of the data becomes memorized. Some of it sticks into the AI model a bit stronger than you would like, and either you don't notice or you don't quite care about it, and you wind up publishing your AI, releasing the model into the world. Perhaps you're selling it to other businesses, or you're publishing it for free use, or you're in some other way sharing it with other people. And along this way, the AI finds its way into someone's hands who maybe it shouldn't have, and they decide to attack it. They try to figure out stuff about the sensitive secret data you showed it during training, and there's various things you can try to figure out, and I'll get back to those in a minute. But the key is that they get access to something, some form of information about your secret data. Depending on what the data is and what they get out of it, this can be really bad or it cannot quite matter. But it's something that's worth keeping in mind. So, what are these things you can actually get out of a neural network? There are three main types of attacks you can do on them. The first one is called a property inference attack. In this case, we try to figure out how was the data. We try to answer questions about mainly the distribution of the data. For example, was the gender split even in the training data, or was it racially different? This is something that makes us maybe unable to trust the AI base to operate in new areas. The second type of attack is called a membership inference attack. In this case, we try to figure out if a particular piece of data, an image maybe, was used in the training data. Perhaps I'm curious if my Instagram images have been used to train an image classifier, and I use my own image inside this membership inference attack to try to figure out if it actually was included. And the third type of attack is the reconstruction attack. This is the most complete of the attacks, and it tries to actually conclude and refine the entirety or a subset of the original training data. So whereas the other ones were trying to find out information based on data, the third one is trying to reproduce it entirely. And it's this third type, the reconstruction attack, that we'll be focusing on and talking about today. Before we move on and talk about the state-of-the-art reconstruction attack, we'll just mention real quick that all of these attacks are very model dependent. As I mentioned before, there are a lot of different types of AI. You have ChatGPT and image classifiers and stable diffusion for images. All of these take very different inputs and give very different outputs. And because of this, you need to adapt the methods you use for all of your attacks. So what I've been focusing on this summer and what I'll be talking about today is image classifiers. These are a form of neural network which take in an image, like this person on the right. Then they try to fit this into various classes and figure out what is inside the image. This one, for example, tries to recognize if it's Ada, Ben, or Tia that's in the image. And it seems to consider this to be 5% likely to be Ada, 80% likely to be Ben, and 15% likely to be Sia. So this is what the image classifier does. It looks at an image and tries to figure out what class does it belong to and with what probabilities. The classes can be anything. For example, it could be dogs versus cats, different dog breeds, or for most of the focus of today's presentation, it will be faces. So the AI will be trained to recognize 1,000 different celebrities. But moving on to the main attack itself, the state-of-the-art attack at the moment is called a GMI attack, or Generative Model Inversion attack. It works roughly like this, in that it takes in a classifier it's trying to attack, and then it takes in auxiliary data, and hopefully it spits out training data. The classifier it takes in has of course been trained on some form of data. For example, these images of celebrity faces. And then the auxiliary data used should be similar to that training data. For example, in the case with celebrity faces, we'd use maybe scraped regular people's faces from the internet as auxiliary data. And if it was a classifier for cats and dogs, we'd use scraped images of cats and dogs, and so on. The more similar we can get the auxiliary data to the training data, the better results we'll get. And this attack, in general, assumes full access to the classifier, which means that you pretty much have a downloaded version yourself on your computer, and that lets you look into the brain of the AI model when you're trying to attack it. So you can figure out exactly how to do the best possible job. But taking one step into the GMI attack, we see this. It's 3 different parts working together iteratively to get the best possible results. We have a GAN creating synthetic data, which we use to calculate the loss and iteratively improve the entire process. Now we'll go through these 3 little detailed steps. The first of them is the GAN. A GAN is a generative adversarial network, which is an AI system trained to generate images. The way it's trained is it competes with itself, but that's not too important at the moment. What is important is that we train it on the auxiliary data. So using the auxiliary data, we create a new GAN, which is able to generate images similar to that of the training data that we give it, the auxiliary data. And this image generation process is very similar to that of diffusers, which have grown popular lately, like Midjourney, Stable Diffusion, or DALL-E 2. But these systems, if you've used them before, take in a text input, generally speaking, like for example, a fish on Mars, and then they spit out an image, like the cute fish you see in the middle here. In contrast to the diffuser system, the GANs instead take in a long list of numbers, a coordinate system in space, pretty much, and then they turn that into an image. Changing the coordinate space will change the image, and giving the same image coordinate space will give you the same image. So by changing the input to the GAN, we can change the output. The reason we're using this GAN is that we're trying to get as realistic results as positive in our attack. Avoiding this step has been tried, and then you get really noisy results, generally speaking. But using this GAN is what the generative parts in GMI comes from, and it allows us to get far more realistic and good-looking results, as long as the training data is close enough to the auxiliary data. Moving on to the next step, the GAN generates some set of images of whatever we're trying to reproduce. For example, it could be faces. Like, let's say it's generated this image right here. It's an attempt at generating a training image from the datasets. And to start with, it won't be particularly similar to anything in the training datasets. This is expected, and we'll work from there. Once we have one of these synthetic data points, an image that we've generated, we calculate what's called a loss. And the loss is a form of quality measurement of the image. The more the image we've generated looks like we want to reproduce, for example, if we're trying to reproduce a chihuahua, the more it looks like a chihuahua, the smaller the loss. And the less it looks like a chihuahua, the bigger. So we want as low a loss as possible. Once we have this loss, we do a form of iterative optimization. We use the fact that we have access to the entire classifier's brain, and we have access to the GAN's brain, and we look at these and we try to figure out how do we change this input to the GAN to improve the images, lower the loss, and make it more similar to whatever it is we're trying to reproduce. Then we take a small step in that direction in the coordinate space, and therefore getting a result that's more similar to what we want to reproduce. Then we keep looping this system, calculating a loss, checking how do we make this better, and keep going this way. And we can see that we started with this image, then we got a second and a third, and these are results from a run I did this morning. So we can see that in the end it stabilizes after a few hundred steps on this image of a person. It's quite different from the first one, but it looks far more similar to the one I was trying to reproduce, I promise. So this is the way that we wind up getting access to the main data. While this is the main loop of the GMI attack, there are deeper steps into it, more things going on in the background. We won't look at most of them, but we'll have a quick peek at my personal favorites. This is a look into the one more depth of nuance and detail. Won't be looking at all of this, and all of it isn't important for today. The part we'll be looking closer at is this called consistency selection up in the top right. It's a layer between the synthetic data we generated and what we actually consider to hopefully be training data. So let me show you an image. These are 40 faces, all of which are trying to reproduce the same person. As you might be able to see if the images are big enough, they are quite different, and it's a bit unclear without any form of context which of these are actually good. And in a real world scenario where you're attacking the system, you wouldn't of course have the training data at hand to check with. So instead you'd have to make do with just these images to try and figure out which are actually the best ones. So the general purpose here is to get the best recreations possible. And the first step for this is that instead of generating just a single image per end result image we want to get, we'll generate several copies. For example, if we want to get one image of a person, maybe we generate 4. Let's say these 4. They're all attempts at generating the same person as we saw before. And then we'll select the best possible image out of these 4. And the first step to finding which of these is the best is to look at the secondary subsets. Using the classifier, we check not what does this look the most like, because it's going to look the most like whoever we want it to look like. But who does it look the second most like, and the third, and the fourth, and the fifth? So like, what are the second most similar things, and the third, and so on? For example, these could be similar to person 1, 2, 3, and 4, 1, 7, 8, 9, 1, 2, 3, 5, and 1, 2, 3, 6, respectively. Next, we try to find a subset of these which share these secondary classes. Looking at these, we can see that 1, 2, and 3 appear in both the third, the first, and the fourth image, whereas the second one doesn't share those same classes. So therefore, we discard the second image, which wasn't included in this subset of shared second categories. Then we have 3 images left, and to pick between these, we just look at which the original classifier we're attacking is most certain about, which it thinks looks the most like the person we're trying to reproduce. Let's just say it's the image on the right. And in this way, we've gone from having 4 images which we're all attempting to look like a single person, to the images which hopefully looks the most like the person. And the general thought behind this is that there's similarities between classes. For example, if you were trying to reproduce me, it would be more likely that whatever you get out of it looks like my brother than it looks like my fiancé. And if you were trying to reproduce an image of a dog, it's more likely to look similar to a cat than it is to look similar to a tree. So in that way, we'll look at what are the second and third and fourth most similar things. And if they share similarities, they're probably closer to being what we actually want. But this is the only detailed, more high-techy thing we'll be looking at for the GMI attack at the moment. And instead, let's move on to some results of actually testing this on a few more systems. So what you see here are the results from a GMI attack that I tried to do on one of these classifiers. Before we analyze the image further, I'll just talk a bit about what was I actually attacked, the classifier in question. So the target classifier was trained with 1,000 classes, and each class was a celebrity, and they were each their own class. So it learned to see the difference between all these 1,000 different people, each of which had around 30 images. And just to mention, the entire network had around 60 million parameters, and there wasn't any augmentation done on the training data. If you don't quite get what that means, that's not an issue, and it's not too important, but I figured I'd mention it for completeness sake. So, going back to the actual results of the attack, we can see that the left-hand side of each pair is a recreated image. Those are the ones that have been created by the GMI attack with no information about the training data. The right-hand side is instead a image from the training data set that's been paired with the recreated image. As you can see, not all the pairs are complete. That's because not all the recreated data could find a suitably close match in the training data sets. The colors and stuff we'll be getting into in just a second, but in my opinion, at least, looking at these on a sort of wide spectrum, the attack looks fairly successful and the people look fairly similar to what we've been trying to recreate. However, to make this a bit easier to quantify, there are two metrics that have been tested, but it's quite a difficult thing to measure these attacks and the success. There's no standardized metric used in the scientific community. But the most common one is one called accuracy. Accuracy tries to answer the question of recognizability. If we try to generate 100 images of dogs, and then we think that 60 of them actually do look like dogs, the other ones look like trees or cats or fish, then we get an accuracy of 60%. So accuracy is just the percentage of images which actually look like what we wanted them to look like. And since there was 1,000 different celebrities, and I'm pretty awful at celebrities, and the fact that there were a lot of images generated to test these attacks, we use another classifier to evaluate the results. So we train a second classifier on the same images as the classifier we're attacking, and hopefully it learns to recognize the same people. Then it gets to look at the end results of the attacks and see, does it agree with what we try to reproduce? Does it think the thing we try to have a cat actually looks like a cat? And if it does, we give it a green background. If it doesn't, we give it a white background. So in this case, the image on the right would be in agreement with the attempts, and the image on the left wouldn't be a fit. Next up, we have a small metric of similarity. Whereas the first accuracy metric just looked at the recreated image themselves, the similarity looks at the image matches, the pairs between the recreated images and the original training data images. First of all, these pairs are formed if the training data image, the recreated image has a training data image of the correct class, so the same person, in the top 100 most similar data points from the training data. Then we compare these two images of hopefully the same person, and we check how similar are these pixel-wise. Pretty much how similar are the images themselves. We use a metric called SSIM for this, which is slightly more complex than just looking at pixels, but not all too much. And if this is a sufficiently high value, we give them this sort of red border around themselves. But with this in mind, going back to look at the results, we can see that the accuracy, the main metric used in academic papers, of this attack wound up at, I believe it's 85%, the amount of images that are green, and this is at a state-of-the-art level. Similarly, the similarity is at around 37.5% in this case. But to get a bit more of a feel for it, let's just give a small brace of hands looking at the top 3 images on the left. How many of you would consider them to look like the same person within the pairs? No hard feelings either way. Raise a hand if you think they look like similar, the same person. Yeah. Some people do, some people don't. It's roughly 50-50. That's a good result, I'd say. But then if we were to zoom in on the people, we'd see them like this instead. And let's just take a moment to look at them again. And give me another raise of hands. How many people think they look like the same person now that they're a bit bigger? pretty much a decent bit of people now as well. Always fun to do live stuff. Generally speaking, people consider them to look less similar when they're sized up. Here it was roughly the same. But I believe that's likely due to the fact that when they're smaller, we try to fill in the blanks with the mind, and when they're bigger, we spot all the strange differences. So this is another thing that makes these results fairly difficult to evaluate, and what is dangerous will depend a lot on context. To get a bit more numerical results, the groups were combined randomly. So celebrity 1 and 2 were paired up randomly, celebrity 3 and 4, and so on, to reduce the number of classes, but still keep the same number of data, to see how the number of classes would result and affect the results. And this gave us, for example, this is a result of attacking for 500 classes, where they're in random pairs. In my opinion, at least, the pairs which are made look roughly as good as they did before, but we can see that the accuracy is a fair bit lower, so it's more difficult for the system to recreate similar looking stuff. And we have a case for the 100 as well, but it's not too interesting to look at. We can give you a moment, but we'll move on in a second. Plotting these results, we get two cute graphs. The one on the left shows accuracy and how that changes with number of classes. It's worth noting that a random image will get 1 over the number of classes as accuracy. So, for example, in the case with just one class, all images would always be of the correct class. And in the 2-case class, 50% will just be right automatically. But we can see that it seems to roughly stabilize at around 45% mark as the class increases, and then pop out quite a bit for the 1000 case. This can depend on a lot of stuff. For example, that I've done my hyperparameter optimization at 1000. And it can also depend on the fact that the image classes are better split for 1000. And it's easier to try to recreate something the more disparate it is. The graph on the right instead shows the percentage of cases which are both accurate in that they're considered the same by an evaluation classifier, and that they are of the correct similarity, so that they have a high similarity score with the image from the training dataset. This is a bit less correlated with the initial attack, but still quite highly. It also seems to stabilize at a fairly low level, maybe around 0.3, and is far less affected by the spike at 1000, which seems to indicate that it's more the accuracy increasing rather than the similarity between the images. Also, another test was made, grouping the people on features instead of grouping them randomly. So while the first one grouped people randomly, this one would group them on features such as smiling and male. Using these two, for example, we'd get 4 classes. We'd have smiling and male. We'd have not smiling and male. We'd have not male but smiling, and not smiling and not male. So the results from this are somewhat different. These are the results from that attack, and we can see that the accuracy is really high. It's 100%, doesn't get much better. But looking at the pairs, at least in my opinion, they are generally a bit worse off than the initial pairs. Likely this is because of the generalization I talked about before. This recognizing traditionally male and recognizing smiles is a far simpler task than recognizing the randomly selected and joined celebrities. As such, the AI system, when trained, doesn't have to learn as much about each individual image. And in the initial system, you'd likely get a spike on the probability that it's correct when we get close to a training image, whereas in this case, where it's mostly learning to recognize smiles and it's learning to recommend traditional male features, you get less of a spike and therefore less of a result. We have similar graphs here as in the case before, with the accuracy being higher than the last case, but the right similarity score being pretty much constant, and likely just due to random combinations of the large number of datasets. So just going into a few final closing thoughts. This is very much an evolving set of methods, an evolving field of work. The state-of-the-art stuff I've shown and talked about here are all less than a year old, And the general feel of trying to recreate training data in this way just started around 5 years ago, and then it wasn't even looking at neural networks, but just regular statistical analysis. So it's difficult to say where it's going to go and what's it going to do in the future. But in general, the attack seems to get good accuracy, but be worse at recreating exact images. And even for a well-generalized system, the accuracy remains really high. So if this is something that should worry you or not, that depends a lot about the field of work you're in, how sensitive your data is, and what you're going to do with it. But either way, I'm just going to mention three closing ideas on simple ways to protect yourself against both this kind of attack and the other types I mentioned before. The first of them is to self-host your model if you can. Instead of giving out full copies of your AI, maybe host it on your own server and let people run inference on that. This means that people can look into the brain of your AI when they try to attack it and get it to do stuff for them, which makes the process a fair bit harder. The second is sort of based on you self-hosting in the first place, and that's to round your results. Perhaps if you have an image classifier, maybe people don't need all the detailed numbers. Maybe they don't need to know that it's a 98.25768% likely that it's a cat. Maybe you can just round it off to 98%. And doing this sort of rounding will make the system a lot more robust to the kind of optimization attacks that were done here. Lastly, as we could tell in the last examples where we looked at the images which were trained on the faces and male, the attributes, a system that is well able to generalize is far more better protected against getting identical images out. Therefore, keep in mind to regularize the models when you train them. If you don't know what that means, no worries. But if you do, it's good stuff, not just to increase your accuracy in training scores, but also to keep your data safe. So with that said, thank you very much for listening.
Thank you so much. Do we have any questions? No, don't be shy. Do we have any questions in the chat? No? Okay. Oh.
Like the example that you have shown, it's specifically focused on an image. And I was wondering whether it is possible to use it on like different source of data and how much the approach will differ. For example, if I have no, it's. I was thinking more like we have a big company, and to simplify the life, I make this AI that goes through all of the documents, so it knows exactly where to look for. This is like good for like lawyers and similar. And then like there is also, but to make it easy, I also put the customer cases also there. And is it possible? How much will it differ to like trick the AI to give me the information that, as an attacker, I would like to see?
Yeah. So your example was like an indexing system, right? Using an AI roughly.
Yeah.
Yeah. For example, using an indexing system, for example, you'd imagine still that it would result in more certain matches whenever it encounters something that looks similar to perhaps when you have a particular quote from a case that would give it a really strong reaction to point you to that particular case. And the sort of beauty with this attack is that as long as you can generate this form of examples well, you can figure out if it works. But in this case, you need to have a system that would generate text inputs instead of generating these images instead of the GAN. So it would likely still be possible. I've seen similar work on diffusion models and trying to figure out what's in them. And I know there is research on text models as well, but I haven't read it myself. But it should be perfectly possible.
One more question.
What do you think about effect of augmentation on the data for protecting it? I think if we augment the data, it will make it harder for regenerating it. Do you think like that?
I'd agree. Yeah, certainly.
Yeah, so
I-
that's another way to protect it.
Absolutely. I think augmenting the data is, I mean, it's just good practice to do either way. And I think it will, just like other regularization paths,
Yeah,
it will
exactly.
help a lot with protecting it.
Any more questions?
So you said that you trained a GAN network. How similar must this training data for the GAN network be to the original training data?
That's a very good question, and it's very crucial to the entire attack itself. Since all the images you get out are generated by the GAN, it has to be able to generate images sufficiently similar to the training data. If, for example, we're using this facial example again, and the training data consists of a wide range of people, but the auxiliary data I've used to train the GAN is just selfies of me, for example. Then all the images generated will just be selfies of me, and maybe I'll get the selfies of me that are most similar to you, for example, but it won't be particularly good. A more realistic example would maybe be using the auxiliary data as just white males, whereas you have a good spread in the original training data. You'd still just be able to get out the people who were actually white males.
Right. So the auxiliary training data must simultaneously be similar enough to the original training data, but also general enough that you can get more specific as you go.
Yeah, pretty much. The more similar you can have it to the original training data, the better. And if you have any gaps in your auxiliary data, you'll have those same gaps in the results you get.
Right. Thank you.
Okay, so question is, how do you proceed from here? What should be investigated as a next step?
Well, there's quite a lot of things that I think would be interesting to look more at. Looking at, for example, in all these test cases, the amount of data has been constant. It's always been 30,000 images. Looking at how the amount of data affects would be really interesting. More data should make the attack less vulnerable, since it should be able to generalize better. Another thing that would be interesting to look at is using augmentation, like we talked about, see how that affects it. Would also be really interesting to look at specializing a form of attack that uses fine-tuned models. A lot of stuff these days is based on fine-tuning publicly available models, and as such, in these cases, you'd have the original model still available, and I believe it's likely you could use that to enhance your attack. Look at where the differences come in and what it reacts extra heavily to create extra vulnerabilities. While that's not too much about the GMI attack itself, I think that would be a really fascinating thing to look at.
All right. Any more questions? Okay. Thank you so much, Elliot.
Thank you very much for having me.
The next Tech Tuesday will be held with SICK IVP on September 19th, when Johan Melander from Department of Electrical Engineering at LiU will talk about image sensor semiconductor technology. Make sure you sign up today. Thank you so much.